Let's take a look at another periodic trend. Okay. Now let's remember, periodic trends are properties that we can determine or make predictions about based on the location, the position of an element on the periodic table. Okay, so let's look at what we call electronegativity. Okay, it's a trend on the periodic table. Now, what electronegativity is? It is the attraction of electrons to an atom when a bond is formed between two atoms and a molecule is formed. Okay, so what we're looking at is electronegativity is a property that comes into play when you form chemical bonds between different atoms and you want to know who in the bond is really controlling or attracting those electrons to themselves. I often think of it as the greediness in a chemical bond. Which atom is the greedy atom and is attracting those electrons? Okay. Now what we see here is we see some numbers. If you notice, they range from about 0.7 down here with the alkali metals up to 4.0 where fluorine is. Fluorine is considered the most electronegative element. Okay, and this scale system was developed by Linus Pauling, and we use electronegativity to help us predict bond type. Is a bond a polar covalent bond? Is it a non-polar covalent bond? Or do we see it as an ionic bond? And so that's what it's often used for. And we can predict this trend. Now with these numbers we can see what is happening as we move across a period. As we move across a period, which remember is a row on the periodic table, we see pretty much a consistent, steady increase in those electronegativity values. So as we move across a period, we see a steady increase. We would see a greater attraction for electrons in a chemical bond. And we notice that the nonmetals here have the highest rating. They're the greedy atoms in a chemical bond. Now as we look in a column, which remember a column is called a group on the periodic table, what we notice is as we go down we see a decreasing in the electronegativity values. So that attractiveness property for electrons inside of a chemical bond decreases as we go down. Okay, now let's look at the far left here at the alkali metals. We notice that there's a nice steady decrease here. Now what we know is as we go down a group, down a column on the periodic table, that we're adding principal energy levels. Our atom is getting a larger radius, and with a larger radius there's a greater distance, so that attractiveness for valence electrons to the nucleus is less. Okay, so it would be further away, so it's harder for that nucleus to attract and hold possession of those electrons that it has on its own valence, and then those that it would obtain inside of a chemical bond. And as we go across a period, we see that increasing pattern of electronegativity, that greater attraction. Well, we know that as we go across a period that there is a decrease in radius, which would help give proximity to the nucleus so that that electron could be attracted. But we also know that as we go across a period, there's a greater effective nuclear charge, that the nucleus itself is gaining protons and becoming more positive. Okay, it's that effective nuclear charge is increasing. And so there's going to be a much greater attraction for electrons. Okay, so there's our trend. Our trend is as we go across a period, electronegativity increases. As we go down a column, down a group, we see a decrease in electronegativity. Now, let me show you an example of how we use electronegativities to predict bond type. Let's use, for example, a carbon dioxide molecule. Okay, a carbon dioxide molecule has a carbon-oxygen double bond. Here's just the bonding scheme of it, and there are lone pairs of electrons on each one of these oxygen. Okay, there we go. Okay, so now if we want to predict that bond type, is it polar, covalent, nonpolar, covalent, or ionic? What we do is we use the Pauling scale to determine that. So we take the electronegativity values, okay, 2.5 for the carbon, okay, 3.5 for the oxygen, and we just simply take the absolute difference. Okay, the absolute difference is 1.0 between those. Okay, the absolute difference is 1.0. That's what we call the electronegativity difference. Okay, now on the Pauling scale, when the electronegativity difference is between 0.4 and 1.7, okay, when that difference is between those two, between that range, we consider that a polar covalent bond. Okay, so it is a covalent bond, but there's unequal distribution, unequal sharing of the electrons. Okay, so this would be a polar covalent. Now let's take, for instance, how about sodium chloride, a table salt? Okay, we've got the bond between those two. Okay, sodium is a 0.9 on Pauling scale, and chloride here you can see is a 3.0. Okay, let's take the absolute difference. The absolute difference is a 2.1. Okay, when this electronegativity difference is greater than 1.7, okay, when the electronegativity difference is greater than 1.7, we consider that an ionic bond. Okay, anytime the electronegativity difference is greater than 1.7, and some include 1.7, it would be considered an ionic bond. And we know that ionic bonds are typically found in metals and nonmetals, between those two. And then let's take an oxygen molecule, for example, an oxygen molecule. So we've got an oxygen to oxygen double bond is what we have. And we've got lone pairs there. Okay, so this would be 3.5 minus 3.5. Absolute difference is 0. So if the electronegativity difference is between 0 and 0.4, we consider that a nonpolar covalent bond. Okay, a nonpolar covalent. And we would see equal distribution, equal sharing of those electrons there. Okay, so we consider that a nonpolar. So in summary, the electronegativity values, Pauling scale, help us predict that bond type. Okay, are we seeing ionic bonds? Are we seeing covalent? And if they're covalent, are we seeing a polar or a nonpolar nature? Okay, and we see that metals are typically lower in electronegativity values, and nonmetals are typically higher. Okay, nonmetals would be considered the greedy, the attractive atoms of the electrons in a bond, whereas the metals would be those considered the losers of the electrons in that bond. Okay, and one final time, let's go over the scale, the range of values. If the electronegativity difference is between 0.4 and 1.7, we consider it a polar covalent bond. If that difference is greater than 1.7, we consider it an ionic bond. And if the difference is 0 to 0.4, we have a nonpolar covalent bond.